Welcome back. In this video, we'll be taking a look at the concept of chemical reactions. The first topic we'll take a look at here is just exactly what a chemical reaction is. Chemical reactions are events that occur when chemical bonds are either formed, rearranged, or broken. These get represented as chemical equations using a particular written style known as molecular formulas. When there's a subscript, a little number written to the side of the atom, it indicates how many atoms are there and that the atoms in this formula are joined together by bonds. A prefix number, a number in front, tells how many unjoined atoms or molecules are around in the equation. And our chemical equations will contain reactants. These are the things in the reaction that are reacting together. Meanwhile, on the right side of the arrow, we will see the product, which are the things that are made as the chemical equation progresses forward. Here are a couple of examples of this. We have reactants on the left, products on the right. The arrow indicates the reaction happening and is sometimes said as the word yields, Y-E-I-L-D-S. The first example has two hydrogen atoms. When we have a reaction between two hydrogen atoms, those being our reactants, what we get from that, our product, is hydrogen gas. Notice that the H is now written with a subscript 2 that indicates that the two hydrogen atoms have been joined together to produce a hydrogen molecule. In our second example, we're going to add together 4 hydrogens. Notice the prefix there, those are individual hydrogen atoms, plus a single carbon atom. And when we have that reaction occur, then we'll get a methane molecule, a carbon with 4 hydrogens attached to it. The H2 and the CH4 are both molecular formulas. So two nice examples of chemical equations written out nicely. Reactants on the left, products on the right, and the arrow representing the equation happening or the reaction happening. There are 3 main ways chemical reactions can happen, either synthesis, decomposition, or exchange. In the synthesis reaction, we're making new bonds. In a decomposition reaction, we're breaking old bonds. A great example of something you might consider decomposition would be digestion, and we'll certainly get to that in AMP2. Exchange reactions both make and break bonds, and they do exactly what the name implies. They exchange atoms between molecules. Let's take a look first at synthesis reactions. If we have 2 atoms, an A and a B, we can add those together and have a reaction which combines those two, giving us a single molecule of A linked to B. In synthesis reactions, atoms typically combine and make larger, more complex molecules. They always involve bond formation, and we describe this kind of reaction as an anabolic reaction if it's happening in a living system. So in a cell, in a body, the word anabolic and the word synthesis effectively mean the same thing. Here is a picture of what that might look like. In a synthesis reaction, we take individual pieces, like amino acids, and join them together into larger molecules, such as proteins. And if you notice the picture on the bottom, the individual little units are connected by lines, and those lines represent bonds. So this is a great graphic example of a synthesis reaction combining small pieces into larger molecules by making bonds between them. Next, let's take a look at decomposition reactions. These are reactions that break bonds. So we have large complex molecules being broken down into smaller pieces. In the example on the screen, we see a molecule represented by the letters A and B. And in the reaction, those are broken apart. So we have 2 smaller pieces now. The A is separate from the B. This is sort of the reverse of a synthesis reaction. It always involves breaking new bonds, and if we're in the body, in a cell, we would also use the term catabolic. So inside a living system, the word catabolic and decomposition, again, are relatively equal. Our next slide shows this happening, and we have a nice example in the middle of the screen. This is a large starch-type molecule called glycogen, sometimes called animal starch. You don't need to necessarily know that right now, but we'll get there later on. And if we break that apart, we get individual pieces. In this particular case, those individual pieces our glucose molecules. We'll talk a lot more about this particular reaction later on. You actually store glycogen as a energy storage mechanism in two main places in your body, your liver and your skeletal muscle. More about that a little bit later on. In an exchange reaction, again, we do what I'd said before. We move pieces around. In the example on the screen, we start with an AB, an A linked to a B by a bond. We bring in a C part. And again, for the moment, realize these A's, B's, and C's are just placeholders for other items. What we're going to do in this example is we're going to take the B off of the A and put the C on the A. So we quite literally exchanged or swapped out the C for the B. These are sometimes called displacement reactions. They involve both making new bonds and breaking old bonds. So this is actually a synthesis and a decomposition reaction happening at the same time. Here's a picture of that happening. We see ATP transferring a phosphate onto a glucose in this particular picture. In the top molecule, we have an energy molecule that we'll talk about a lot in this course. It happens to be a molecule called ATP. It's got 3 phosphates on it. On the right-hand side, we see a glucose, and the lower reaction shows a phosphate being transferred from the ATP over to the glucose. So we have broken a bond by taking a phosphate off the ATP, and we've made a new bond by attaching that phosphate to our glucose to create a new molecule called glucose phosphate. Exchange reaction. Another set of reactions that we'll discuss a lot as our semester goes by is a group of reactions known as oxidation-reduction reactions. These are all decomposition reactions. Digestion is a great example of these. Reactions that occur when food fuels are broken down for energy are typically going to be oxidation-reduction reactions. They're also exchange reactions because electrons are moved around between reactants. In an oxidation-reduction reaction, we're always going to be removing electrons from one place and moving them over to another place. Molecules called electron acceptors get electrons. Molecules that receive electrons are being reduced. And a good example that we see here is C6H12O6, which happens to be glucose, plus some oxygens, will give us 6 carbon dioxides, 6 waters, and ATP. In this particular reaction, the glucose is oxidized and the oxygen molecule is reduced. And there's a handy little mnemonic, a handy little memory aid to keep in mind here. I'll bring it up on screen in just a moment. And what you need to realize is that some pieces lose electrons, some pieces gain electrons. Those pieces that lose electrons have been oxidized. Those pieces that gain electrons have been reduced. So if you're ever asked in a question, which of these items is oxidized and which of these is reduced, ask yourself, did it lose or did it gain electrons? The handy little phrase here is Leo the lion says grr. Now, that's appearing on screen right now, and yes, I realize that that is probably not how you would spell grr, but just bear with me. L-E-O, lose electrons, oxidized. G-E-R, bad way to spell grr, but it works here. G-E-R, gain electrons, reduced. So hopefully that will help you keep this straight. If any atom or molecule is losing electrons, it is being oxidized. If it's gaining electrons, it's being reduced. Here on this slide, we'll take a look at energy flow in chemical reactions. All chemical reactions are described as either being exergonic or endergonic. This gonic word effectively means energy. Exergonic reactions leave or lose energy. They release energy, and this is common of catabolic or oxidative reactions. A great example for you of an exergonic reaction is a chemical hand warmer. You can actually buy these in places like Walmart or a lot of sporting goods store. A cold winter day, maybe you're out skiing, maybe you're out just enjoying the cold weather. And you have this little packet that you bought at the store. You take it out of its package, you crinkle it up, and all of a sudden it is chemically releasing energy. That would be a great example of an exergonic reaction. Another example of an exergonic reaction would be a reaction in a tube. think of Halloween. A lot of little kids walking around the neighborhood, and many of them have in their hands this plastic tube full of liquid. It's a glow stick. And you probably have on occasion had a glow stick that you take the tube, you bend it over so something inside breaks, and all of a sudden light is being released. Well, light is a form of energy, and that is a chemical reaction that is releasing energy. It's an exergonic reaction. The next topic there, endergonic reactions. These require energy for the reaction to take place. A good example there would be mixing together in a bowl in your kitchen things like flour, cocoa powder, eggs, a little oil, a little sugar, pinch of salt, and effectively making cake batter. Well, if you put that cake batter in the oven without turning the oven on, all you have an hour later is just cake batter. On the other hand, if you turn the oven on to an appropriate temperature to cook the cake, you add energy in the form of heat from the oven to that cake batter. You change it. You chemically change it into cake. That is a great example of an endergonic reaction. And in my head, the way I usually keep that straight is you need to put energy in an endergonic reaction in order for the reaction to take place. Chemists will tell you that many chemical reactions are reversible. In fact, in theory, all chemical reactions are reversible. Chemical reactions get to a state known as equilibrium, or a state of balance, where there's no more movement forward or backward. But the reality is, in a living system like your body, most biological reactions are irreversible. You can't turn them backwards, and a lot of that is due to the fact that they take an enormous amount of energy, but they're also the reality of the fact that a lot of these biological products are removed from the system by organs like your kidney and your liver. How fast do chemical reactions happen? There are several things that affect the rate of chemical reactions. Temperature is the first one. As temperature increases, reaction rates tend to get faster. The second is the concentration of a reactant. Keep in mind one important item here. In order for two atoms to bond to each other, to stick to each other, they literally have to touch. And the more pieces there are around, the more likely they are to touch, so the faster they will happen. Imagine being in a room, a fairly large room, like maybe an auditorium, with 10 other people. What are the chances at any given moment that two people are touching in a very large room when there are only 10 people in the room? Kind of small. On the other hand, take that same size room and put maybe 300 people in it. What are the odds that two people at any given moment are touching? Pretty high. So the more reactant pieces you have in a system, the faster reactions occur. The next item is particle size. The smaller the size, the greater a rate of reaction tends to be. This is one reason why things are often ground into very small pieces in order for a reaction to happen. Things like a firecracker, if you look at the powder, the gunpowder inside an individual firecracker, they're very, very fine particles. They tend to react much faster if they're smaller particles. That has to do with surface area, but that's a concept we'll talk about later on. Now, the next concept, the last one on the page, is catalyst. Catalysts increase the rate of energy without being chemically changed themselves. Enzymes happen to be biological catalysts, and we'll talk a lot about those a little bit later in this chapter. But effectively, a catalyst, as I said a moment ago, helps a reaction happen faster, but does not itself get changed in the reaction. That's going to finish this particular topic. We'll pick up again with the next video. Thank you for your time.